Welcome to Introduction to Ecology, Lesson 14. In the last unit, we talked a lot about populations, about population growth, about population decline, about changes in populations over time, which is what we call population dynamics. But the focus of everything we did in the last unit was single populations. Now we're going to take a step back and look at an expanded view where we consider multiple populations at the same time. We're going to look at what we call species interactions, what they are and how they actually affect population dynamics, how two or more species interacting with one another can change the way that those populations behave through time. Today we're going to focus on predation, and that's one type of species interaction where individuals of the first species, the predator, consume all or part of individuals of the second species, the prey. This leads to what we call trophic interactions, and these are any interactions that involve feeding or feeding on or eating of another species. Ultimately, trophic interactions can be grouped into food chains, and what we see on the right-hand side is an example of a food chain. So at the bottom of the food chain, we have primary producers. These are autotrophs. Like we learned in the first lesson, these are organisms that make their own food out of inorganic sources. Sunlight frequently, but sometimes it's inorganic chemicals. One level up, we have our herbivores, or what we call primary consumers. These eat the primary producers. These eat the plants and the other things that make their own food. One level above the herbivores, we have carnivores, and specifically we have secondary consumers. So here in this example, we've got a grasshopper eating the plant, that's our herbivore, but then we've got a mouse eating the grasshopper, and that's our secondary consumer, and it's a carnivore. One layer up again, we have another carnivore, but this time it's a tertiary consumer. So here we've got a snake eating the mouse, and one layer further up, we've got what we call a quaternary consumer, a fourth level consumer. That's our hawk that eats the snake. So the hawk eats the snake eats the mouse eats the grasshopper. All of those are consumers. And then the grasshopper eats the plant. And so the grasshopper is the herbivore. The other three are carnivores. The grasshopper and the three carnivores are all consumers. And then at the bottom, we have our primary producer. So when I think about predation, I can actually consider three broad categories. The first is carnivory. With carnivory, the predator is a carnivore, and the prey is an animal. So both the predator and the prey are animals. Contrast that with herbivory. Here the predator, which we call a herbivore, is an animal, so that's the same, but the prey is not an animal. The prey is a plant or an algae or some other primary producer. Finally, we have parasitism. This is a little bit different. With parasitism, the predator is a parasite, which means that it lives in close physical proximity, usually directly on the prey, and the prey is the host. And typically with parasites, they consume only certain tissues. So the example that you see in the picture is actually a mite, and it's a mite that lives on your skin. And this is a parasite, and you are the host, and the mite actually eats your dead skin. These mites come out, they mate on your face at night, they eat your dead skin, and that's their whole life. Now, they're not eating other parts of you. They're not eating your eyeballs, they're not eating your blood, they're not eating your bones, they're only eating your skin, and that's fairly typical of parasitism. A little bit different, we have parasitoids. These are halfway between a parasite and a carnivore. So parasitoids are insects that lay eggs in or on another insect host. And then when these eggs that the parasitoids have laid hatch, the larvae stay in that host, and they usually eat and kill it. They kind of eat it out from the inside. So they're not typical parasites because they actually do eat most or all of their host, and they actually kill it. So unlike the mites that live on your face that only eat your skin, these guys eat every tissue. They don't just eat the skin of the caterpillar, they eat everything. And they kill it. The mites on your skin are not killing you. However, they're not really carnivores either, because most carnivores will take multiple prey of a particular species or in a particular population. If I think about a mountain lion, it's going to eat a lot of different little baby deer. Whereas with parasitoids, they only eat one individual. They spend their entire life eating that one individual and killing it very slowly over time. So they're a little bit in between. They're sort of a weird, is it a parasite? Is it a carnivore? Who knows? All right, so now let's contrast carnivores and herbivores. So the first thing that differs, this is pretty obvious, is that carnivores kill their prey. If you see this wolf pack here, it's attacking an elk. That wolf pack is going to kill the elk before it eats it. Herbivores don't tend to kill their prey, at least immediately. This giraffe is not going to kill the eucalyptus tree before it eats it. And in fact, eating the eucalyptus tree is probably not going to kill the eucalyptus tree. Sometimes herbivores do kill the plants that they eat, but typically that's when the herbivore population gets really, really high and ultimately damages the plant because there's so many of them. Most herbivores aren't great for the plants, but they also don't kill them. With carnivores, the prey can run and hide and can escape. With herbivores, that's not the case. The prey are stationary. They're typically plants, so there's not much they can do. Plants can't run. It's kind of hard to hide, so they have to have other strategies to avoid being eaten. With carnivores, the prey are actually more nutritious than with herbivores. Now, I know everyone tells you that vegetables are good for you, they're nutritious, and that's true, but in the natural world, typically what's most limiting is nitrogen, not carbon, nitrogen. And so prey items that are high in nitrogen are very valuable. They're much more nutritious than prey items that are not high in nitrogen, that are maybe higher in carbon relative to nitrogen. And so animals, as they eat, accumulate nitrogen. And so as you move up that food chain, you get more and more nitrogen. And so at the bottom with the plants, they don't have a lot of nitrogen. You have to eat a lot of plants to get the nitrogen you need. Versus if you're eating a higher animal where you're getting a lot more nitrogen. And so carnivores, because they're eating animals, are getting more nitrogen, and so that's more nutritious, and they have to eat sort of less of it to get what they need. So this leads us to the idea of diet preference. Ultimately, diet preference depends on two factors. It depends on the encounter rate, and it depends on the handling time. So the encounter rate is the time that it takes to search and find prey. That whole looking process, the whole sort of, trying to find these hidden prey that are cowering down. Handling time is the time that it takes once you've found the prey to kind of catch it, subdue it, and eat it. And really we have two different classes of strategy. If your encounter rate is low, that means it takes a long time to find the prey. You got to spend hours searching for every single prey. And in that case, you want to take whatever you can get because it's so hard to find the prey that you just grab whatever you see. That's if the encounter rate is low. But if the other strategy, the handling time might be high, that means it takes a long time to sort of eat the food. Maybe that's because the food is low in terms of nutritious value, so you got to eat a lot of it. Maybe it's just because it's really hard to get at that particular food item. But if the handling time is high, then you don't want to just take whatever you can get because you're going to invest a lot in that item that you choose to eat. And so you want that time to be invested well. You want that time spent wisely, and so you only want to eat things that are going to be really good for you. So ultimately what that means is if your encounter rate is low, you're going to be a generalist. You take whatever you can get because it's so hard to find anything. But if your encounter rate's high and the handling time is high, you want to be a specialist because it's easy to find stuff, but you don't want to waste time on just anything. You only want to eat the stuff that's going to really pay off. Now, not surprisingly, this distinction is sort of a difference between carnivores and herbivores. With carnivores, I have a mobile prey that can run and hide, so it makes it a lot harder to find. And that makes your encounter rate really low. You spend a lot of time looking for those hidden or running animals. On the other hand, the food that you do get, each animal that you do get, is quite nutritious. So that means you don't have to spend as much time sort of eating the animal. You get a lot more bang for your buck, a lot more nitrogen in particular for the time you spend eating the animal. So in this case, we have a low encounter rate, but also a low handling time, and so we're going to tend to be generalists. If I take a look at the other scenario, if I think about a herbivore, my plants that I'm going to eat are stationary. That means they're easy to find. I can walk outside and see a ton of plants that I could eat. However, the plants are not super nutritious, right? They don't have a lot of nitrogen in them. You're going to have to spend a lot of time eating shoots in order to get the food that you need, the nitrogen content that you need. And so in this case, we have the opposite scenario where we have a high encounter rate, but also a high handling time, and so we want to be specialists. And that's what you see here. We've got the panda that specializes on bamboo. If you walk through a bamboo forest, it is not hard to find bamboo, but you've got to eat a lot of it. The handling time is very high to get the food you need, and so these guys tend to be specialists. All right, so that's prey preference. But before we move on, I want to talk about how we measure prey preference, because it might not be obvious. So preference is eating one or a few species more than would be expected based on chance. Now, it doesn't mean just eating one species more than another, right? That's not preference. And I'll give you an example. So here in this particular field, we have 2 deer for every 1 rabbit. If I have a mountain lion, it comes in on Monday it eats a deer, on Tuesday it eats a deer, on Wednesday it eats a rabbit, on Thursday it eats a deer, on Friday it eats a rabbit, and on Saturday it eats a deer. Overall, this mountain lion, if you add it all up, has eaten 2 deer for every 1 rabbit. That's what you would expect if you just blindfolded the mountain lion and let it eat whatever it ran into. There's no preference in this scenario because it's eating deer relative to rabbits in exactly the same ratio as we have present deer relative to rabbits. Let's contrast that with another scenario. Here again, I've got my 2 deer for every 1 rabbit. But let's say on Monday, the mountain lion comes in and eats a rabbit. On Tuesday, he eats a rabbit. On Wednesday, he eats a rabbit. On Thursday, he mixes it up and eats a deer. And then on Friday, he eats a rabbit. So in this case, the mountain lion has eaten 1 deer for every 4 rabbits. So this ratio is different than what you would expect just based on chance encounters. And in fact, the mountain lion has eaten a lot more rabbits than you would expect. He really should be eating 2 deer for every 1 rabbit, but instead he's eating 1 deer for every 4 rabbits. So he's eating a lot more rabbits than you'd expect. He's showing preference for the rabbits. Now, contrary to that last example, most carnivores do not show preference. And again, that's because they have this generalist strategy. It's so hard to find mobile, running, hiding prey that you just take whatever you can get. That's not entirely true. There are some predators that do show, some carnivorous predators that do show preference for a prey species. A classic example is lynx. Lynx will preferentially eat snowshoe hares even if other things are more available. Even if there's a lot of squirrels and groundhogs and birds that they could eat, they don't eat those as much. They actively seek out snowshoe hares even when snowshoe hares are quite rare. Another case where we do have preference, but it's a little bit different, is where we have what we call switching. And this is where the carnivore will actually prefer what's most abundant. And again, that's a preference. That's not just sort of eating what's most abundant because it's more abundant, so you're just going to run into it more by chance, right? This is preferentially selecting the most abundant species. So if I have 1 deer for every 2 rabbits, the carnivore might eat 1 deer for every 4 rabbits. It's accentuating that difference. But then if I come back a couple years later and I have 2 deer for every 1 rabbit, the carnivore might now switch and eat 4 deer for every 1 rabbit. Again, it's accentuating the difference, but it's always going in the direction of the difference. So if I have more rabbits, it's going to eat preferentially more rabbits. If I have more deer, it's going to eat preferentially more deer, but it's actually going to accentuate the natural difference that's just there in the populations. So why would you do this switching? There's a couple reasons. First, you might have a search image. You might get locked on to this thing that's common, and so you that's what you're looking for, and you kind of ignore the other stuff. Another possibility is that you learn how to find or how to handle or how to deal with the abundant thing, and so that makes it easier for you to catch it, and so you tend to eat that more. All right, so that's carnivores. Herbivores are different. Again, herbivores are eating stuff that's easy to find because it's stationary, it's plants, but not as nutritious, so we have a much higher handling time. And so most herbivores are specialists. And they're specialists in a couple of different ways. First, they tend to be specialists on specific plant parts. They don't just eat the whole plant. Now, that's not true of some large herbivores, a lot of mammals and birds. They will eat the whole plant. So here's a rabbit. It's not being real picky. It's eating a flower. It will also eat the leaves. It'll eat the stems. If it can get down there, it might even eat the roots. But the vast majority of herbivores are not, in fact, large mammals. In the world, the vast majority of herbivores are things like insects. And the vast majority of these actually do specialize on particular parts of the plant. So here we have an example with an aphid. Aphids do not eat leaves, they do not eat crunch on the roots. What aphids do is they stick their stylet into the stems and they suck up the phloem. They suck up the sort of sap from the phloem. And so they are specializing on the stems, they're specializing on the liquid in the plants. And again, that's very common of insect herbivores to specialize on one part of the plant. In terms of which part of the plant most herbivores specialize on, the leaves are specialized on more than any other part of the plant. And there's a number of reasons. First, leaves are abundant. If I think about a plant, there's a lot of leaves for every stem, for every, maybe root, things like that. Or at least leaves are quite accessible relative to the roots. In a lot of places, leaves are available year-round. Even here, we have some plants that have leaves year-round. And also leaves are very nutritious relative to other parts of the plant. They're actually the most nutritious part of the plant except for seeds. So we have a lot of insects that specialize on leaves, actually a lot of invertebrates in general that specialize on leaves. What does this do to the prey? What does it do to the plant? Well, it can do a number of things. It can reduce growth. It can actually reduce survival. It can kill the plant. That's not as common, right, as with carnivores that always kill their animal. Prey, but it does compromise survival, and it can frequently cut down on reproduction. So here's a good example. We have a gypsy moth and a forest, and gypsy moths are classic defoliators. What that means is they eat the leaves of the plants. Now they don't kill the plants, but if you actually look at the growth rings in years where you have gypsy moth outbreaks, you'll see that they're smaller. The tree did not grow as much. It was stressed. It didn't have the leaves out to photosynthesize because the gypsy moths had eaten them all. So again, that reduces growth. During these years, the plants don't put out as many seeds, but typically it does not kill the trees, or most trees survive through a gypsy moth outbreak. And so you come back the next year and they've got all their leaves and everything's happy again. But for that 1 year, there was no leaves on the trees because the gypsy moths ate them all. All right. So not all herbivores eat leaves. We have what we call below ground herbivory. If you dig up plants, you'll frequently find little grubs on the roots, eating the roots. A lot of these are beetle larvae, but they can be other things. We also have seed predation. This is my favorite example of seed predation. These are pogonomyrmex. There is actually a species of pogonomyrmex in South Carolina, only one. The vast majority are out west. But these guys specialize on seeds. They collect different seeds from certain plants, and they bring them back to the colony, and that's pretty much all they eat. We also have some animals that specialize on the internal fluids of the plants, so like aphids. Another related insect, these are scale insects. They're absolutely terrible. They don't really look like insects, so you might not recognize what you've got on your plant, but these guys basically lock on. They don't move a lot. They sort of stick their mouth part into the plant and they suck up the plant juices, and that frequently does kill the plant. So if you see these on your houseplants, not a good sign. All right. Not only do herbivores specialize on specific parts of the plant, but they tend to specialize on specific plant species. So again, this is not universally true. It's less common with your larger herbivores, your mammals, your birds, although pandas are a good example of a mammal that's very specialized on just bamboo. But in the figure, or in the picture there, you see we have a squirrel that is currently eating the Reese's peanut butter plant. So yes, it's quite a generalist. It will take most things. But again, thinking about the vast majority of herbivores that are invertebrates, not mammals and birds, things like insects, they do specialize on one or a few plants. And so a classic example are these monarch butterflies. Those are the caterpillars for monarch butterflies. And those of you who heard about monarch butterflies declining, you'll know that people tell you plant milkweed to save the monarchs. The reason you want to do that is because milkweed is the only thing that monarch caterpillars can eat. It's really the only plant they can live on. And so they're specialists on the milkweed, and that's why you want to plant milkweed to save them. All right, so that's herbivores. Carnivores, again, are much more general. They tend to eat all sorts of different things. But we do have different classes of carnivores, and that's typically based on the way that they get their prey. And very broadly, we can divide carnivores into those that sort of move around and search for their prey, and those that sit and wait for the prey to come to them and then attack it when it does. So even within a particular group of carnivores, like spiders, we have both strategies represented. In the top, you see our jumping spiders, our salticids, and you see wolf spiders, and these guys are really fast, and they jump, and they freak a lot of people out. Although, honestly, who doesn't love the jumping spiders? They look like teddy bears. But the reason they run fast and they jump is because they are trying to hunt down the prey, and their prey is mobile. It's other running arthropods. And we can contrast that to the other two spiders in the bottom. We have a black widow and a barn spider, and these guys tend to just sit around and wait for prey to come to them. So I always say, if there's a black widow with a web in the corner of your room, I wouldn't leave it there, but I wouldn't be super concerned because that black widow is not going to be running all over your room. It's pretty much just going to hang out in that web, even if you turn off lights and go to sleep. So again, that's because its whole strategy for living is to sit there and wait and conserve energy and let the prey come to it. Same with the barn spiders. The barn spiders wait for the prey to get caught in their net. And barn spiders are like Charlotte in Charlotte's Web. All right, so that's carnivores, herbivores, sort of some of the things that they do in terms of their strategies. Now let's talk about their adaptations. What allows them to be good predators or good or not good prey? So with predators, the adaptations we have a number of different strategies for catching prey. The figure there, that picture you see is a house centipede. This is not my favorite arthropod, and one of the reasons I don't like it is it runs really, really, really fast. The reason it runs fast is because it has a body form that allows it to go really fast so that it can catch the prey that it's eating. It's actually eating other invertebrates that are living in my house. And it's running fast in order to hunt them down. Other adaptations that some predators have, so things like snakes, maybe they don't run fast, but they have jaws that are good for biting and catching and swallowing. And so sometimes if you see these snakes, you'll think, how is that prey item, how is that mouse or rat or whatever it's eating ever going to get into that snake? But they can actually kind of open their jaws really wide and get that animal in, and they can chomp down on that animal and hold it until it's dead. A lot of things like snakes also have poison to subdue the prey. So centipedes have poison, snakes have poison, scorpions have poison, some spiders have poison. And again, sometimes those poisons are venomous to you, but frequently they're more just to kill the prey so that they can eat the prey. Hurting you is sort of a secondary thing. Another predator adaptation is mimicry. So this is where the predators blend into the environment. And I think this is a great example. That picture where you see on the right, the farthest right is a flower, and the thing that looks like it on the left is actually a praying mantis. And this praying mantis is attempting to catch insects that come to the flower to pollinate it. So typically the insects that pollinate this flower get confused and try to mate with it. But when they try and mate with the mantid actually catches them and eats them. Another predator adaptation, this is an unusual one that your textbook mentions, and so I'm going to use the exact same example that your textbook does, partly because this is quite unusual, is inducible traits. So some organisms will adjust to match what their prey is. This example is a ciliate protist that actually changes its size to match the size of the prey. So when the prey it's eating is bigger, it'll grow, and when the prey it's eating is smaller, it'll shrink so that it can sort of eat that particular prey that's available. Finally, a lot of predators have the ability to detoxify or tolerate the chemical defenses in their prey. Again, this is a classic scenario in herbivores. And going back to the monarch caterpillars, monarchs eat milkweed. A lot of other caterpillars cannot live on milkweed, and that's because milkweed produces a toxin. And the monarch caterpillars actually take that toxin and sequester it and use it to their own advantage. We'll see that in a few slides. But other caterpillars can't do that, and so they lack that ability to be a predator for the milkweed species. All right, so that's the predator adaptations. That's what allows predators to be good at hunting down prey. What allows prey to escape? Well, those are prey adaptations, and there's a number of ways that prey can deal with trying to avoid being eaten. One is that prey can just be big. So back where I come from, in Canada, we have a lot of moose. And there's a saying in Canada that if you get into a car accident with a moose, the moose will walk up and get away and you'll be dead. So it's very different from a deer. If you've ever seen a moose, they are not like deer. They are huge. And one of the reasons that they're big is that they need to defend themselves against wolf packs. And the way they do it is they actually kick wolves to death. And that's because they're big enough to be able to sort of stomp the wolf to death. And just a word of warning that they will also stomp you to death if they think you're a predator, if they think you're a threat. And so we actually have moose can actually be more dangerous than grizzly bears. People don't realize that because they will actively try to kill you. So I said deer are a little bit smaller than, or quite a bit smaller than moose. Deer don't have that large size advantage. What deer do better than moose is they run. Deer are really, really fast. You would be hard-pressed to keep up with a deer. And that allows the deer to get away from the predator. That's the adaptation that deer have in order to avoid things like wolves and coyotes. All right. Other prey has different strategies. So some of them produce poisons. A good example is the monarch. It doesn't actually produce its own poison, but it takes that poison from the milkweed and it sequesters it and it uses it, and it makes the monarch terrible tasting to things like birds that would otherwise eat it. Now, of course, it's not great for the monarch to be terrible tasting if the bird keeps trying to eat you, right? So frequently in combination with poisons, prey species will develop what we call aposematic or warning coloration. So the milkweed is monarch is not orange and black to be pretty. The monarch is orange and black to warn birds that it's going to taste terrible to eat it. And so once birds learn that eating an orange and black butterfly is not a good idea, they will avoid those butterflies. Of course, that leads to sort of a different strategy for avoiding being eaten, and that is mimicry. So the butterfly on top is a monarch. The butterfly on the bottom is not a monarch. It's actually a viceroy. And a viceroy tastes great. A viceroy does not have those toxins from the milkweed plant. It's actually good food for birds. But it looks a lot like monarchs. And you can look at those, and it's hard for us to tell the difference. You can imagine a bird with their little brains. They're like, that looks like a monarch to me. I better not eat it. And so this is mimicry that helps to protect the viceroy, even though it doesn't have any poisons or any bad taste. There's two different kinds of mimicry. One is crypsis, where you tend to camouflage in with your environment so that the predator can't see you or can't find you. The other is this false advertising, where you look like something that's unpleasant, and so the predator thinks they don't want to eat you even though they really would. Another prey adaptation is behavior changes. So certain prey will actually forage less when there's predators around. A good example is fire ants. So one way that we've learned to control fire ants is by introducing a parasitoid, something we talked about earlier today, a parasitoid phorid fly. And for a while, people thought that these phorid flies were actually killing fire ants. It turns out they are, but not really that effectively. What the phorid flies are actually doing is preventing fire ants from foraging, because the fire ants are so busy trying to protect themselves from the phorid flies and trying to hide and cower from these phorid flies that they can't go out and collect food as easily. And so it's that behavior change that means the colony doesn't grow as well, it doesn't produce as many babies, and that's what cuts the fire ant population down. It's not the direct killing of the phorid flies so much as this change in behavior that the fire ants adopt in order to avoid being predated on by these parasitoids. Another behavior change, muskoxen will form circles to sort of protect the group from predators. And then we have animals that send off warning cries. It's another kind of group behavior. Things like prairie dogs will start barking if there's a hawk or an eagle flying over the colony, and then all the other prairie dogs around will kind of dive into the holes and hide. And so again, that's a way that the prairie dogs avoid being eaten by certain birds. The final example of a prey adaptation is what we call predator satiation. And the best example I know of this is periodic cicadas. We've talked about those before in this class. We'll probably talk about them again. They're amazing animals. But these guys come out every 13 or 17 years in sort of en masse. There's just all of them come out together over a period of 2 weeks. They mate and die. And the reason they do that is because the predators that are flying around can't eat them all. They eat a few and they get full, and then they sort of let the rest of them go and they mate and they live their life. And then for the next 12 or 16 years, there's no more cicadas. So the bird population can't respond to that huge influx, because even if it grows in that 1 year when there's a lot of cicadas, then it'll decline over the next 12, next 16 years, and so it can't really capitalize on it. So that's predator satiation. All right, what you'll notice about the prey adaptations we just finished talking about is that most of those primarily apply to animals. But remember, we said that animals aren't the only kind of prey. Plants can be prey too, and plants are prey in plant-herbivore interactions, when we have sort of a herbivore eating a primary producer. And so not surprisingly, plants also have ways to avoid being eaten, just like the animals we talked about in the last slide. One way that plants avoid being eaten is masting. This is essentially the same as predator satiation. This is where plants produce many, many, many seeds in one year and then very few in the next couple of years. So again, the plant predators, the seed predators, can't capitalize on that because their population responds in the 1 year and grows really well because there's tons of acorns, but then the next 2, 3, 4, 5 years, there's nothing there to eat, and so the population declines again, and then we get another mast year, and the oak trees that tend to mast manage to get some oak acorns that survive and grow into trees because the predators can't eat them all. So masting is very common in plants, especially oak trees. Another thing that plants do is what we call compensation. So this is where removal of the plant tissue stimulates the plant to produce new tissue. If you've ever had something like a basil plant, you'll know people tell you, oh, well, prune the plant to cause it to bush out. That's compensation. Basically, you are the herbivore predator, and you are eating the basil plant, and when you remove the leaf, the plant actually grows more in response. And again, this is a way that the plant deals with being eaten, and there's different mechanisms where this can happen. But one way is that when you remove those top leaves, you expose the underleaves to more sun, and that allows them to grow more. So one particular form of compensation is what we call full compensation. This is where there is no net loss of plant tissue. If I remove some plant tissue, the plant grows exactly that much back in response. So even though it's being eaten, its size would be the same whether it was being eaten or not, because every time it gets a chunk eaten, it grows that chunk back in response. Another way that plants deal with being predated on is through phenology. So a lot of plants will produce leaves at times of the year when the herbivores that tend to eat them are scarce or not around. Maybe it's too early, it's too cold in season for the herbivores to emerge, and so the plant can sort of get the leaf off. And you might think, well, we talked about leaves and we said they're always around. Well, that's true, but the best leaves are frequently the ones that come out in early spring. They tend to have less toxins in them, they tend to be sort of less tough and leathery, and so those are the really good ones for the herbivores to eat. They're the easiest to eat, they're the most nutritious, and frequently what that means is the plants will try to do bud bursts. They'll try to get those leaves, those early spring good leaves out before the herbivores can get to them. The final two categories of plant defenses are basically just barriers. They're just things that stop the plant from being eaten. The one is structural defenses, so being tough, having spines or thorns or these terrible hairs that you see on some plants around here that cause you to break out in a rash. Even things like poison ivy tends to have these sort of defenses. We also have chemical defenses. Again, with poison ivy, the itching is typically caused by a chemical defense. These are secondary compounds. So any chemical that the plant makes for defense, we call it a secondary compound because it's not necessary for just growth. It's only necessary for the secondary process of defending the growth. And so these tend to be toxins. We talked about the monarch caterpillars eating milkweed, but the milkweed has a toxin that prevents most other caterpillars from eating it. So that's an example of a secondary compound. Sometimes, though, the secondary compounds are a little more complicated or a little more tricky. Some of these chemicals that the plant releases don't kill the herbivore directly. They actually call in things like predators or parasitoids that then kill the herbivores. Now, there's two different ways that these defenses can be expressed, both structural and chemical. The first is constitutive. That means it's always on. So this is more common with structural defenses. If I think about roses, the rose always has thorns, right? And that's because it doesn't matter whether it's being eaten or not, the rose just makes thorns in case. That's a little different from what we call induced defenses. These are defenses that are only turned on or only turned on strongly when the plant is being eaten. This is a good strategy if the defense is costly. So it can be very costly to make some of these poisons, some of these secondary compounds. So it doesn't make sense to make them and spend all that energy making them if you're not being eaten. And so what a lot of plants will do is they'll turn on production of the toxin only after there's been some plant damage, only after the plant knows that it's in trouble, and so maybe it's worthwhile to make the toxin. So that's what plants do to prevent being eaten. Of course, the things that eat them, the predators that eat them, which is the herbivores, have ways of overcoming these defenses. So in terms of overcoming structural defenses, a lot of animals will just learn to avoid or tolerate the sort of barriers. If I think about cacti, a lot of cacti are eaten by little desert mice or desert rats. And what these animals do, they either eat around the spines or they actively remove the spines so that they can eat the plant. It's harder to actively remove poisons or toxins, but there's ways of getting around it. So a lot of insects that eat otherwise poisonous plants actually have digestive enzymes that break down those poisons. Another possibility is maybe they don't break down the poison, but maybe they become unresponsive or insensitive to it. So frequently, venoms and toxins and poisons work by binding to a critical enzyme and then stopping that enzyme from working, and that kills the animal that was trying to eat you. But what animals that overcome these sort of toxins do is they evolve enzymes that the toxin can't bind to, and so the toxin is useless in these organisms. We also have behavioral adaptations. So in this case, the animals sort of act in a way that makes the defense less beneficial. A good example is with pine beetles or bark beetles. A lot of bark beetles will attack things like lodgepole pines. And if one or two attack a lodgepole pine, the lodgepole pine's response is to produce a lot of sap and kill the insect. But what bark beetles do in order to overcome this is they produce a pheromone that calls all the bark beetles from the neighboring area together and causes them to attack a single tree en masse. And when they do that, they overwhelm the sap defense of the tree, and so basically some of the bugs are killed, or some of the beetles are killed, but a lot of them manage to get in and eat the plant and kill the plant. All right, so not surprisingly, we've talked about coevolution before. Coevolution is common in plant herbivore systems. Coevolution is basically that evolutionary arms race, that reciprocal evolutionary change in interacting species. So I have a plant, and it makes a toxin that prevents it from being eaten. Well, then the herbivore says, well, that's not good, I can't eat this plant anymore, and so it evolves some mechanism for either dealing with the toxin or breaking the toxin down. What does the plant do? It says, oh, I'm being eaten again, that's not good, and it evolves a new toxin that the herbivore is not resistant to. And so we go around and around and around in this circle, leading to this sort of, like I say, evolutionary arms race where the plant tries to avoid being eaten and the herbivore tries to make sure it can eat that plant. All right, so those are sort of the broad classes of predation and the different ways that predation occurs and the different adaptations that allow predators and prey to interact. So now we're going to change focus, change gears, and we're going to look at what predator-prey interactions do to population dynamics. We've seen this before, I think in one of the last few classes. We saw that predator-prey systems, like the lynx and the hare, can actually cause cycling or cyclical fluctuations in the abundance of the predator and the prey. And this is probably the first example, the most famous example, is the lynx and hare system. And it was sort of studied intensely, especially in Canada, because of the Hudson Bay Trading Company. So this was a fur trading company that essentially built Canada. And they were really interested in knowing about the cycles in the lynx and the hare because they were trying to use the hare for fur. So they would send trappers up to northern Canada to hunt snowshoe hare, and what they found is that some years it was great. They found tons of snowshoe hare, and that was a good year. But then other years they couldn't find hardly any snowshoe hare. And they really wanted to understand why, what's going on. And not only that, they wanted to be able to predict when it would be good to go out and hunt for hare and when it just wasn't worth sending people out to look for fur. So ultimately, this led to what we call the Locke-Volterra predator-prey model. Now we're going to study a couple of different Locke-Volterra models. This one is the Locke-Volterra predator-prey model. And again, this is a set of differential equations. Each one of these is a differential equation, but we will not do calculus in this class. We will not integrate these equations. We will not take derivatives of any equations. There's no real calculus going on, but I do expect you to understand what these equations say. So the first equation is the equation that describes the population dynamics for the prey population. Unfortunately, predator and prey both start with P, so we're going to use N for prey, and we're going to use P for predator. So the first equation, again, is a differential equation, dn dt, and that means it describes the rate of change in the prey population size as a function of time. The bottom equation is, again, a differential equation. It's dp dt, so it describes the rate of change of the predator population through time. So let's break this down. If I take a look at the first equation, let's say there's no predators in the system. Let's say p equals 0. Well, in that case, I have an equation that should look familiar to you from the last unit. That's actually the differential equation for exponential growth. And again, you don't need to know how to integrate it, but you do need to know the integrated form of that equation. That's just what you used on the last test. That's your exponential growth equation. right? And not surprisingly, that little r is the same as the little r we learned about all last unit. That's the exponential growth rate. So the assumption of the Lacca-Volterra model, the Lacca-Volterra predator-prey model, is that the prey population grows exponentially in the absence of a predator. Now, we know that that leads to unlimited growth, but when we add a predator, when the p is not 0, when we have at least some predators in the system, then we don't have exponential growth anymore. We actually have a negative term on this equation, and that's because the predators are removing prey, right? Now, how do the predators remove prey? Well, in the Lacca-Volterra model, we assume that they do this according to mass action. What that means is that the encounters or the predation rate between predators and prey increases linearly with both the number of predators and the number of prey. Let's take a look at that. What that means is basically if I have 4 deer in my population and 1 mountain lion, maybe the mountain lion eats 1 deer a day. But if I double the number of deer, now I have 8 deer, my mountain lion is going to eat double the number of deer in a day. So now the mountain lion is going to eat 2 deer a day because now there's 8 deer rather than just 4. Same kind of deal, if I have 1 mountain lion and 4 deer, maybe I take 1 deer a day. But if I double my mountain lion population, I double my predator population, again, I'm going to double the rate at which the prey are taken because each mountain lion is going to take 1 deer. All right, so that's mass action. And to get mass action, we basically multiply the number of prey by the number of predator. That's the MP term. What's that little a? Little a is a constant that basically describes the efficiency with which predators capture prey. How easy it is to find prey and hunt it down and eat it. So it's basically an encapsulation of your encounter rates and your handling times. That's sort of how well predators do that whole process of capturing the prey and removing them from the population. All right, so that's the prey equation. Now we're going to look at the predator population. And again, same kind of deal. Let's look at what happens to the predators when we don't have any prey, when n equals 0. So if I do that, what you'll notice is that my differential equation has just a negative term. What does that mean? That means that my predator population declines. It gets smaller and smaller and smaller and smaller. That should make sense. Without any prey, there's nothing for the predators to eat. And so they're going to starve. They're not going to reproduce. They're not going to make babies, and eventually the population is going to go extinct. But good news, if we do have prey, if n is not equal to 0, then I don't just have a negative term, I actually have a positive term in this equation too, that first term. And what that means is that prey allows the predators to breed. It allows production of new predators, and that makes sense, right? The whole reason to eat is to, grow and make babies. So let's again take a look at that positive term. We again have a mass action term, n times p, and we again have that a term, which is how easy it is for the predators to catch prey. So that's basically the rate at which prey are being removed, and what that basically means is that the number of new babies made by the predator population is proportional to the amount of prey they remove. If they remove more prey, they're going to make more babies. So again, that's exactly the same term that we saw in the prey equation. The more prey that are caught, the faster the predator population grows. But we have this other constant, b, and b is the efficiency with which prey are converted into predator offspring. So you can imagine I might be able to catch rabbits and deer at the same rate, right? And so the mountain lion could catch 3 rabbits a day and 3 deer a day, but a mountain lion that's catching 3 deer a day is doing a lot better, right? And so I would expect that we'd have a lower b because it takes a lot more rabbits to make a new baby mountain lion than I would have for deer. I expect a higher b for deer because it takes fewer deer to make a new baby mountain lion to breed than it takes rabbits. So again, that little b is the efficiency with which we turn a prey item into new babies in the predator population. And that really has to do with how nutritious or how much food there is per prey item. All right. So I said you'd never have to integrate these equations and never have to take a derivative. Nobody's doing actual calculus in this course. But you do have to understand these equations and you have to be able to use them in a non-calculus way. And what we're going to do is we're actually going to figure out isoclines. Zero population growth isoclines are conditions where the population size of the prey does not change for a given population size of predators, or the condition where the population size of the predators does not change for a particular size of the prey. That's a little confusing, but we're going to break it down. So if I want to find a prey isocline, I am going to start with the prey equation. This can get confusing, but again, if I want the prey isocline, I want to start with the prey equation. And that's because the prey isocline is the point at which the prey population does not change in size. And remember, dn dt is the rate of change of the prey population through time. So if I want no change through time, I want to set dn dt equals 0. That means that the prey population is not changing through time. So I want to find what predator population makes that possible. What size of predator population do I need to make the prey population not grow and not decline? And basically what that means is I'm looking for the number of predators where that number of predators is taking just enough prey that I'm perfectly balancing the reproduction rate of the prey, right? So I have prey entering the system through reproduction, and I have them being removed through predation. And if I have exactly the right number of predators, my rate of reproduction and my rate of predation balance perfectly, and so I have no net change in the prey population. That's what I'm really looking for. I'm looking for how many predators do I need to exactly balance my reproduction rate and my death rate due to predation. So again, I'm going to set my prey equation to 0 to look for the prey isocline. And then what I'm going to do is I'm going to solve for the predator abundance. That tells me how many predators exactly balance the reproductive rate of the prey so that I have no increase in my prey population and I have no decrease in my prey population. So if I do that, you should be able to solve that equation. The ends cancel out and I just get that the predator population that exactly balances birth rate is equal to little r over little a, which is the exponential growth rate of the prey divided by that efficiency with which predators find and eat the prey. So let's take a look at what that looks like. I'm going to plot prey abundance on the x and predator abundance on the y. And it doesn't actually matter what you put in the x and y. You can flip-flop that. You just got to keep it straight. So if I want to draw the prey isocline, that is when the predator population is exactly equal to r over a. And r is a constant and a is a constant. And so that's a constant, right? And so for whatever prey abundance I put in, I have that same value for the prey isocline. I have r over a. In this case, let's say it's around 8. So that is my prey isocline. That is the amount of predators where the predation rate, that total net loss of animals due to predation, exactly balances the gain of animals due to birth, right? Now, what happens if I have fewer predators? So I'm below the prey isocline. Remember, our predators are on the y-axis, so if I'm below the prey isocline on the y-axis, I have fewer predators. So again, at the prey isocline, I have just enough predators to exactly balance reproduction. If I have fewer predators, I'm not balanced anymore. I'm actually taking less animals from predation than I'm putting in from birth. So I keep adding more and taking away less. Well, that's good for the prey population. That means the prey population is going to increase. Let's look at the other side. If I'm above the prey isocline, again, the predator population is on the y-axis, so that means I have more predators than what I need to exactly balance predation rate and birth rate. So if I have more predators, that means I've got more predation than I have birth. So my birth is not keeping up with predation. I'm losing more than I'm gaining. And if I'm losing more prey than I'm gaining, what that means is my prey population will decrease. All right? Clear as mud? So if the prey population increases below the prey isocline, remember the prey abundance is on the x-axis. And so increasing means moving to the right along the x-axis. So below the prey isocline, I'm going to move to the right. That means the prey is increasing. And that's because at that low predator abundance, I am not predating as much as I'm being born, and so I'm growing. My prey population is growing. However, on the other side, I've got the prey population decreasing. And again, the prey abundance is on the x-axis, so decreasing means moving to the left. There we go. We have the arrows moving to the left. And in this case, I've got more predators than what I need to exactly balance birth rate. And so I'm actually losing more prey than I'm gaining from birth. And so I'm moving down. I'm moving to less prey along the x-axis. All right, so that is the prey isocline. Now let's take a look at the predator isocline. And again, you got to keep it straight. To know the predator isocline, I want to set the predator equation equal to 0. Again, because I'm looking for that point where the rate of change of the predator population through time is constant, right? The predator isocline is the condition where the population size of the predator does not change for a particular size of prey. What does this mean? Well, we know that the predator just naturally dies, but the point where the predator population stops changing is the point where I have just enough prey that the predator can have babies at exactly the rate that it dies. So again, I get that balanced system where the predator is dying, but it's also having babies, and I have just enough prey that the rate at which the predator is having babies, the rate at which it can make babies, exactly matches the rate at which it's dying, so I have no net change in size of the predator population. So again, what I want to do is I want to solve this equation where the predator population does not change through time. I want to solve that for the prey, right? I want to solve that for how much prey do I need to allow the predator to breed just enough to keep up with the natural death rate. So when I do that, again, I get the number of prey equaling the mortality rate of the predator. That little m is how fast the predator just naturally dies, divided by b times a. And remember, a is the efficiency with which predators search and eat prey, and b is the efficiency with which predators turn prey into new babies. So again, that's my predator isocline, but it's actually an equation involving prey. How much prey do I need to exactly balance predator death rate? Let's draw it again. Again, I've arbitrarily put the prey abundance along the x-axis and the predator abundance along the y-axis. So now I've got n equaling a constant. For any predator abundance, I have the same value along that isocline. And so that's going to be a vertical line. Again, this is the amount of prey that allows the predator to breed just enough to exactly match its death rate, so that we have sort of no net change. I have the same rate I have the same birth rate as I have death rate. Now let's suppose we have fewer prey. If I have fewer prey than right along that isocline, that means it's not so good for the predator. It's not getting enough prey to breed as fast. So it's breeding more slowly, but the death rate just keeps happening. So we're putting fewer new predators in because we don't have enough food to breed, but we're still taking a lot out, and so the net we have is a loss. We are going to be decreasing when we're on the left of that isocline. When we have fewer prey than we need to exactly match the predator death rate, then the predator just can't breed fast enough to keep up with its natural death rate, and so the predator population goes down. There's a net loss. If I have more prey, and remember, prey is on the x-axis, so when I have more prey, I'm to the right of the isocline. When I have more prey than I need to exactly balance death rate, that's a great scenario for the predator. It's actually taking in more prey items than it needs, so it's breeding even more. It's breeding more than what's necessary to keep up with the natural death rate, and so I'm putting more into the system, more predators into the system than I'm losing, and so my predator population is going to increase. Again, I have excess prey, which is good for the predator population, so it increases when I'm on the right of that isocline. And then when I'm right on that isocline, it's exactly balanced. My birth rate, I have just enough prey to keep the birth rate up for the predators to perfectly match the death rate. All right, so again, the predator abundance is on my y-axis, so if the predator population is decreasing, that means I'm moving down along the y-axis, right? Remember, the last case we looked at, we were looking at what the prey does, and so we're looking along the x-axis. Here we're looking at what the predator does, so we're looking along the y-axis. And so if the predator is decreasing, that means it's going down along the y-axis. On the other side, we are increasing, so if the predator population is increasing, it's going up along the y-axis. All right, so there's my two scenarios. I got my prey isocline, and on either side of that, we move along the x-axis because the prey abundance is on the x-axis. And then I got my predator isocline, and on either side of that, we move along the y-axis because, again, my predator population is on the y-axis. So now I'm going to put these together. And I'm basically going to put my two isoclines in, and that divides my, my graph into 4 different regions. If I take a look at the first region, in that top upper corner, my predator population is declining, right? I am to the left of the predator isocline, so I have fewer prey, and so my predator population is declining. At the same time, my prey population is also declining, right? Because I have more predators in that system than I need to exactly balance, and so I'm losing a lot to predation compared to what I'm gaining to birth. And so I put those two together, And those of you who forget how to add vectors, you basically just sort of take the vector in the middle. And so I have something like that. It goes kind of diagonal, the blue vector you see right there. So now I look in the bottom quadrat. Again, I still have my predator population decreasing because I still have less prey than I need. So I'm still to the left of the predator isocline. And so my predator population decreases, but what's happening to my prey? Well, now I have fewer predators. I'm below the prey isocline, and so I have fewer predators than I need to exactly balance, and so that allows my prey population to sort of do well. It allows the prey population to go up. So my predator population is going down, my prey population is going up. If I add those two vectors together, I get something sort of in the middle, and I get a blue line like that. Let's look at the next quadrat. Here, I am to the right of the predator isocline, so I have more prey than I need to just exactly balance predator birth and predator death. So my predator population is going to be going up. I am also below the prey isocline. I have fewer predators than I need to exactly balance prey birth rate, and so that's good for the prey population goes up. So both my predator population and my prey population are going up. The predator population goes up along the y-axis, the prey population goes up along the x-axis, and if I draw the joint vector, it's something in the middle there. Final quadrat, again, my predator population is going up because I have more prey. I'm to the right of the predator isocline. I have more prey than I need to exactly balance predator birth and death rate. However, I'm above the prey isocline, which means I have more predators than I need to exactly balance prey birth and prey death. So again, that causes my prey population to go down. That causes my prey population to go to the left along the x-axis. And again, I put those together and I get the blue arrow. So there's my blue arrows, and what you'll notice is they kind of make a circle. I go around and around and around and around. And that's actually the population cycle. So let's take a look at that a little bit more depth. I'm just going to slide that figure over here. And again, I said this is a population cycle. But I've plotted that cycle as a circle where I'm looking at prey abundance along the x-axis and predator abundance along the y-axis. Frequently, though, we think about cycling through time. And so we can also draw the exact same dynamics as what happens to the prey population through time and what happens to the predator population through time. And that's what I've shown on the right there. In orange, it's what's happening to the prey population through time, and in blue, it's what's happening to the predator population through time. But the figure on the left and the figure on the right represent exactly the same dynamics. They're both Lotka-Volterra predator-prey dynamics. And I want to show you how these two different figures are the same. So let's start at the yellow dot, right? At that yellow dot, if you look at the circle on the left, I am starting at my maximum prey abundance. How do I know that? Well, that is the maximum point that that circle gets to along the x-axis. So that's the x-axis is my prey abundance, so that is my maximum size of my prey population. That's where that yellow circle starts. I am not starting at the maximum predator population, and in fact, I'm not starting at the minimum predator population either. I'm sort of starting at the midpoint of the predator population. So what does that mean? Well, if I look at the figure on the right, I'm starting at the maximum prey population. I'm starting at a peak in the prey population, and I'm starting somewhere in the middle of the predator population. I'm not starting at the trough or at the peak. I'm starting right in the middle. So what's going to happen? Look at the arrows. The arrows point that we are going to go to the left and up. So we're going to decrease the prey population and increase the predator population. So let's watch that happen. There you go. You can look at the figure on the left where I move around the circle. I decrease along the x-axis, increase along the y-axis. But then if you look at the time figure, that means my prey is decreasing. There it goes down along the orange line. But my predator is increasing. There it goes up along the blue line. All right, so that takes me to the next point. Now I am at the maximum predator abundance in my cycle. How do I know that? Well, if you look at that circle, I'm at the maximum point along the y-axis, and the y-axis is my predator abundance. So I am sort of as high as the predator population goes in that cycle. Not surprisingly, that corresponds with the peak in the blue line on that figure in the right, where I'm looking through time, right? Now, I'm not at the maximum prey abundance, but I'm also not at the minimum prey abundance. I'm right in the middle of the prey abundance. In terms of that circle where it is along the x-axis, the yellow point is now right in the middle of the circle along the x-axis. So I'm right in the middle of the prey population size. So not surprisingly, if I look along the orange curve in the figure on the right, I see the yellow dot is right in the middle of the prey population size, but it's actually at the maximum of the predator population size. It's at the maximum of the blue line. So now what happens? Well, my prey population is going to decrease, because if you take a look at that circle, I'm going to move further along towards the left of the x-axis. But my predator population is also going to decrease because I'm going to start moving down. So take a look at the left figure. I am moving to the left and down, right? I am decreasing my prey, and I'm also decreasing my predator. Now if you look at the figure on the right, let's take a look at what the yellow dot does along the predator, the blue predator line. It decreases. Let's take a look at what the yellow dot does along the orange prey line. It also decreases. So everybody decreases at that point in the cycle. So now where are we? Now we are at the minimum prey abundance. How do I know that? Because if I take a look at the circle on the left, what you'll notice is I'm at the minimum point on the x-axis that circle ever reaches. And of course the x-axis is my prey abundance, so I'm at the low point in the prey abundance. What does that mean? That means my yellow dot should be at the trough in the prey curve on the right. And in fact it is. If you look, it's right at the bottom of that orange prey curve. I'm at a trough. That's the minimum the prey population ever gets to. I'm not at the minimum that the predator population ever gets to, but I'm also not at the maximum. So I should be someplace in the middle of the predator curve, and that's what you see. On the blue curve on the right, through time, I'm not at a peak and I'm not at a trough. I'm somewhere in the middle. So now let's look at what's going to happen. If I take a look at my circle, I'm going to move to the right, and that means my prey population is going to go up. It's at a trough right now, so it's only up from there. What's going to happen to my predator population? Well, it looks like it's going down, right? It's going down along the y-axis. So if you take a look at the figure on the left, I'm going to move down along the y-axis, but I'm actually going to move up along the x-axis. So my prey population on the x goes up, my predator population along the y goes down. If I take a look at the figure on the right now, what that means is I would expect the predator population is going to go down, so along the blue line I'm going to go down. That's exactly what I see. But my prey population is going to go up, so along the orange line I'm going to go up, and that's exactly what I see. All right, now we're at the next point. This next point is actually the minimum of the predator population. How do I know that? Again, look at the figure on the left and look at that circle. The minimum point that circle ever gets to on the y-axis, well, that's where I am now. So I would expect that I'm at my minimum predator abundance. So for the blue curve on the right, I should be at a trough, and indeed I am. Right now, that yellow point is at the low point on the predator curve, at the low point on that blue curve. But I'm not at a low point or a high point in terms of the prey. I'm right in the middle of the circle along the x-axis, along my prey axis. And so what you would expect is that I'm not at a peak or a trough on the orange prey curve. I'm actually somewhere in the middle, and that's what you see. I'm somewhere in the middle. Now what's going to happen? Well, if I take a look at my circle on the left, I would expect my prey population is going to increase because that's how the arrow points. I'm going to go up towards the right. But my predator population is also going to increase because that's pointing sort of up along the y-axis. So again, look at the left curve. We're going to move up on the x, but we're also moving up on the y. And so what that means is that if I look at my prey curve on the right, if I look at the orange curve through time, I would expect my prey population to go up, and it does. And I would also, expect my predator population to go up, and it does. And that takes us right back to where we started. It takes us to the peak in the prey population and the midpoint or a midpoint in the predator population. And we can go round and round and round again, and we get that repeated cycling where we have the prey peak and then the predator peak and then the prey peak and then the predator peak. So again, that's how these two figures, the one where I'm looking at how the prey abundance changes relative to the predator abundance, and I have no time in that figure, no explicit time. And then it's exactly the same as the figure on the right, where I actually look at the prey population through time separately from the predator population through time. And I want you to be able to understand how those two figures are related. All right, so what you may not realize from this model is that the Lotka-Volterra model actually exhibits what we call neutral stability. What that means is that the size of that circle how big the prey population gets, how small the prey population gets, how big the predator population gets, how small the predator population gets. It actually depends on what you start with. It depends on how many predators and prey you begin with. So if I start the system on this circle, it will go round and round and round on this circle forever. But if I actually started with more prey and more predators, I just sort of put more prey and more predators in the system at the beginning, it would go around and around on a different circle. And if I started with less prey and less predators, it would go round and around on a smaller circle. And so that's neutral stability. Wherever you start is kind of the circle you're stuck on forever and ever and ever. That's not realistic. It is true of the Lotka-Volterra model. The minute you add sort of slightly more complexity to the model, say we assume that the prey population in the absence of predators doesn't exhibit exponential growth, maybe it exhibits logistic growth, then we break down this neutral stability. But what's true is even in these more complex models, we still get this cycling. We still get predators going up and then prey going up, and then predators going up and then prey going up. So even these more complex models, they don't circle at any size of circle. Basically, wherever you start, all of those trajectories collapse onto a single circle that's the same size regardless of where you start. So neutral stability is not realistic, and that's a flaw in the Lotka-Volterra model, but the underlying cyclic dynamics is actually very common in these predator-prey models, even when you make them more complex. So great, models suggest that we can get predator-prey cycling, but is that just math people making up stuff, or does that actually happen in the real world? Well, we began this discussion talking about lynx and hare, and we saw those plots from the Hudson Bay Company back in the 1800s where they actually did observe lynx and hare going up and down relative to one another. But that's one system. So we've actually done a lot more experiments to show that this does happen. One good example is a lab experiment where people took E. coli and they actually engineered them to interact according to a predator-prey model. So one stray acted as the predator and killed the prey, and one stray acted as the prey and supported the growth of the predator population. And what they showed is that in this sort of artificial lab system, they could actually exhibit sustained predator-prey oscillations, where the predator goes up and then the prey goes up, and the predator goes up and then the prey goes up. That's in the lab. We also see a lot of cycles in the field, just in natural systems, where we have predator-prey interactions. So we see cycles with the snowshoe hare and the lynx, obviously. We also see other examples. So pine beetles, we see oscillations between the pine and the pine beetles and the pine trees that they eat. So the pine beetles will have a huge outbreak. It'll cause a crash in the pine tree population. And then over long periods of time, the pine tree population will grow back up. And then the pine beetles will respond, and then we'll have another crash. Voles and lemmings also have cyclic periodicity. And then sometimes we get other interactions beyond predator-prey interactions giving us cycles. One that's sort of kind of like a predator-prey cycle, but more complicated, is tritrophic interactions. So that's where we have plants, herbivores, and then some other layer of consumers. So we have 3 different interacting parties, and we get cycles in those systems too, even though it's not just sort of one predator and one prey. Also, sometimes with predation, if you have social interactions, you can get cycling in some of these systems. So I alluded to this a little bit on the last slide. When we have tritrophic interactions, we don't just have 2 populations interacting, we actually have 3 populations interacting. We have sort of typically a plant, a primary consumer, and a secondary consumer. And so this brings us to this idea that when I think about predator-prey interactions, they're not in isolation. They're actually embedded into larger communities with more species interacting. And so what that results in is sort of a scenario where you have both direct and indirect effects. The direct effects are where the trophic interaction actually influences the growth, survival, or reproduction. So when a predator eating a prey actually impacts the growth of that prey, the survival, or the reproduction of that prey. That's a direct effect. However, frequently when you change the prey that the predator was eating, that actually causes secondary indirect effects in all the other organisms that prey item interacted with. So I think a classic example of indirect effects are with the introduction of wolves into Yellowstone. So we put some Canadian wolves in Yellowstone, and wolves eat elk. So the direct effect was to cause a crash in the elk population. The elk population in Yellowstone was way too high. For many, many years, there had not been enough predators in the system because we had extirpated or removed the wolves. So when we put wolves back in, what we saw was the elk population plummeted. That's the direct effect because the wolves were directly eating the elk. The wolves were not eating trees, they were not eating beaver, they were not really even eating bison. But what we saw is that when we decreased the elk population, we actually had a whole pile of indirect effects because the wolves directly impacted the elk, But then the elk impacted all these other things. And so indirectly, the wolves impacted all these other things. Elk tend to like to munch on cottonwood and willow. So when we decreased the elk population because they were being eaten, we actually increased the population of cottonwood and willow. What that did was it provided cottonwood and willow for all the organisms that like to use that. So the beaver population responded favorably and increased in response to all this willow and cottonwood. Same with the bison population. There was now less competition with the elk because the wolves were eating the elk and not so much the bison, and so the bison population responded positively because of this interaction with the elk. So again, we had the direct effect of wolves on elk, but then we had all these indirect effects of wolves on all these different things that the elk interact with. An example a little bit closer to home is the grassy balds in the southern Appalachians. So initially, scientists believed that these grassy balds were maintained by mammoths or mastodons basically eating and preventing bigger shrubs and trees from taking over. Now, we know that there have not been mastodons and mammoths in the Smokies for a long time, but there have been, until recent history, elk, bison, and deer. And in fact, we're trying to reintroduce the elk. Nobody's trying to reintroduce the bison yet. And so scientists believe that after the mastodons and mammoths were removed, elk, bison, and deer helped maintain these grassy balds by eating away at all the plants that would otherwise encroach. Of course, we removed the elk and the bison. The deer are still there. And then probably what happened was that European settlers maintained the balds by, again, cutting back mountain laurel and rhododendron that would other grow in. And so, again, because we've interacted these interactions, because we've interrupted this trophic interaction between elk, bison, and the shrubbery that otherwise grows in the balds, what we've done is we've prevented these balds from being maintained. And so, believe it or not, Park Services now goes in and cuts back rhododendron and mountain laurel from grassy balds to make sure that they remain grassy balds as opposed to being grown over with trees and forests. And so again, because we've disrupted this trophic interaction between the elk and the bison and the trees that would grow into the balds, we have to do that work now. We have to go in and cut them back. Why do we do it? Well, because of all the indirect effects that the elk had on the animals living in the balds. So the one classic example is there is an endangered endemic spider. It's actually kind of related to tarantula that lives in the balds. It's very small, so you don't need to get excited. But Park Services, part of the reason they go in and they cut back all the trees that would otherwise encroach onto the balds is to keep the habitat for these animals. And again, these animals were depending on that indirect effect of the trophic interaction between elk and bison. All right, so that is our little introduction to predation and to the Lacca-Volterra predator-prey model. And if you have any questions, I'd encourage you to contact me. Otherwise, we will see you in the next lecture.